Good morning.
Hey, Tia Rose, where are you?
I'm good. How are you?
I'm fine. Where are you?
Okay, here I am.
No, I mean, where are you in the world?
I'm in Mexico. We're going to Mazatlan. That's what we're headed to now. We should almost be there.
Okay, cool.
Yes, we
Yeah,
should almost be there. We just came from Puerto Vallarta. Guess that's how you say it.
sounds right. Sounds like fun to me.
And it's funny because we went to a tequila factory yesterday, and then I looked and I said we learned about alcohols. I was telling my family, I said we learned about alcohols, and now look, I'm at an alcohol, I'm at a tequila factory.
Well,
I tried to watch the previous video, and for some reason I couldn't. It was like after like the 17th or 20th, like after the 17th minute, I couldn't hear it or anything.
from the lecture,
Yes.
yeah, I don't know what's going on. I'm using WebEx, and
Okay.
it records because I've set it up to do a recording, but I have no idea why it did some sound, but it didn't catch it all. So
Okay.
we'll see how it goes today. But at least you're live today, and you can hear me now.
Yes. Yes.
So I don't know. I don't
Thank.
know why the recording didn't uh, produce the right audio. That's new to me. But I've
Okay.
never used the recording feature in a long time.
Okay.
But
Okay. Thank you very, very much. I couldn't get on yesterday because I was so off on the time, so I wasn't sure because my cell phone says one time, ship time is another time, the Mexico time is another time. So I didn't know what time it was.
well, you got it. You got it dialed in now, so we'll try to do the same thing on Friday.
Okay. Okay. Thank you.
You're welcome. And
Okay.
I'll just wait for people to show up. But I'm ready to go. Uh, so you can see the board pretty well in the video,
Yes. Yes, I
and
could.
stuff's big enough on the board
Yes. Yes. Thank you. Yes, it is.
because the last time I did this, the fluorescence lights created kind of a lot of distortion on the board. So I
Oh
just
no.
didn't know if that was still the case or if you could see it well. So that's
No,
good to know.
I could see it well. The only thing it was just, like the sound, and it was like at the 17th one. I said, well, what happened?
Yeah.
But from the beginning, I'm glad you said what chapters it was. So I was like, okay, chapters 10 and 11.
Yep.
So if anything,
And uh, from the test three preparation, there was a few pages that we didn't get to for test three.
okay.
They're on test four, which is the Grignard reaction. Oh, we went over that on
Okay,
Monday.
okay, yes. Okay, the Grignard reaction.
Yeah, there's some problems on the Grignard on that test three preparation. But I'm trying to put together another file for test four preparation, and I'll include that again.
Okay. Is anyone there yet, or
Nope, it's just you and me.
okay? um, how can I find out how I did on my test?
Um,
Oh dear.
162 out of 200, so 81%.
Okay. Okay, thank you. I was really nervous about that test.
You're pretty good on the first page.
And it was addition, and I know, and I underlined. I know I did. I underlined addition, and I circled
Yeah,
elimination.
you
So
did. The rest of page 2 looks pretty good. Page 3 you did great on. Uh, you had issues with the regio versus stereo selective concept. And,
you said ratio versus selective, right? Okay.
yep. And number 12, the Markovnikov. Good morning, Tasha. Guess where Tia Rose is?
Good morning, Tasha.
She's in Mexico drinking tequila.
Good morning,
Morning.
Tasha. I can't hear her.
Oh, you got to walk up so the microphone gets you. You can get on camera. You can do the lecture, Tasha.
Good morning, Tasha.
How you doing?
I'm doing okay. Doing okay.
Thank you.
I told you, I hate to miss class, so
I'm saying, look, have fun, enjoy yourself.
thank you. Look, Tasha.
Yeah.
We went to on a tour yesterday, and it was a fiesta, and all of a sudden the fiesta had like a tequila thing, and I said, ain't this a kick? I said, I had to laugh because I said we're learning about alcohols, and now I'm here at a tequila factory.
Yes, yes. Hey, Valeria.
Hi.
Hi, Valeria.
Hi, are you sick too?
Oh no.
No,
Oh.
what's wrong?
Oh, I have COVID.
Oh, poor baby.
Oh no.
You need anything? I can do a quick run and drop off.
Oh, thank you. No, my husband, he's negative somehow, so he's the one taking care of everything.
Okay, well, feel better.
Thank you.
Yeah. When did you find out? I'm so sorry.
Monday morning, I lost my sense of smell, and then I got tested later that day.
Oh my gosh. I'm so sorry.
Yeah, I have to be out for 10 days, so I probably won't be back until next Friday.
I hope you feel better.
Thank you. I feel much better. It was headaches were pretty bad. Um, just really congested. But I feel better. My oxygen never dropped, so that's good. And I'm taking vitamins.
Oh, good. Good. No, I'm in Mexico.
What?
I'm on a cruise.
Oh, that's fun. Enjoy.
Thank you.
So were you online on Monday too?
I'm sorry. Oh, no, I had to watch it from the YouTube because the timing was all off. So like I didn't know like the ship time is one time, my cell phone time was another time, Mexico time was another time. So I was just confused at when Eastern Standard Time was. so
Yeah,
I
I
so I
went to get
couldn't
tested
catch
around
on.
class time, so I couldn't come, but I did get the videos.
Did your video like at number 17 or 18, did it kind of like you couldn't hear it or anything too?
Yeah, at the beginning it was hard to hear, and then I put my headphones and it was a little bit better, but it is hard to hear.
And then when it got up to 18, mine just kind of like stopped.
Mm, I'm not sure. I wonder if it was glitching too, because it was hard to hear. Sorry.
Oh no, you're fine. Well, I can hear the congestion. I am so sorry.
It's okay. At least I didn't get like a really bad case. It's more so like
Yeah.
not being contagious to you guys. It just sucks because I
Are
was
you,
supposed to start a new job, so now I'm waiting on that.
oh no. But you know what? God allows everything to happen for a reason.
Yes,
So
yes.
everything happens for a reason. Are you taking elderberry and vitamin C
Yeah,
and zinc?
I have to take it now, but yeah, I taking zinc, vitamin C, vitamin D, uh,
Elderberry.
elderberry, and then I have like two other pills that my husband's mom gave me that they're supposed to be good for you. And I don't know what that is. And then I'm taking one
And
aspirin a day just to be safe.
okay. Oh yeah. Yeah.
But I just started taking the aspirin yesterday. I mean, yeah.
All right, we're
Uh,
gonna do oxidation today. Ready?
yes, we're ready.
Okay, this is gonna fall under kind of what we did Monday. How we make alcohols. No, today is more about what we do with them or their reactions. So we're basically gonna study these four categories. One of them's gonna be a review. One of them's gonna be really easy. And these two you definitely don't want to confuse with each other. So when we say oxidation, there are literally hundreds, if not thousands, of potential things that cause oxidation, also known as oxidants or oxidizing agents. So to keep things succinct for us, if you see that chromium-6, that's your sign that we're doing oxidation. And the chromium-6 oxidations are always done in acid. If you go to other texts, you may see manganese-7 as an oxidant. Those will be done in base, but for us, I'm always going to use that as your sign that we're doing oxidation. And while that's up there, what we don't want to confuse oxidation with is dehydration. So dehydration, the reagent system is always going to be acid and water, and then some sort of heating. And we'll get to the details of that in a minute. So starting off with oxidation, if we look at that, or that, are they the same thing? And you would all shout out methanol. And the mechanisms of oxidation can be quite in depth. You're not responsible for a mechanism, so the key is overall what's going to happen. So you're just responsible for the overall outcome. And if we look at that structure and the initial product, we say the overall outcome is oxidation, which you can see as this system or that system, or also you may just see it like that. That all means the same thing, do oxidation. And when you're oxidizing an alcohol, you're removing two hydrogens the two atoms that lost the hydrogens, you input a double bond. So if we go with, did this O lose an H and did this C lose an H? And are we going to stick a double bond in between the C and the O, which lost the H's? So if we look at this, that H and that H are still there. This C is now doubly bonded to that O, and those two H's are gone. So for oxidation, for most alcohols, you're initially going to lose the H off the O and the H off the C connected to the O. And then you're going to put a double bond in between that C and that O. And so if we go with the question, what functional group is that? Aldehyde. So that alcohol oxidizes to an aldehyde. And that's relevant because aldehydes are also pretty easily oxidized. And the chromium 6 reagent is a very potent oxidation agent. So we wouldn't really be able to isolate that. It's going to further oxidize to the carboxylic acid. And so in this transformation, what would you say you're doing? I would call that an O insertion. So you're just inserting an O in between this C and that H. For practice, if we oxidize this alcohol, what would be the reagent system that you would use? Chromium 6 and acid. And once you see that and this, which two H's are you going to strip off? For sure, you're going to strip off that H. And will you strip off an H on the C, which bears the O? So in this example, I didn't draw in that H. Could you, if you wanted to? Could you draw them both in? And do you lose both of them or just one? Just one. And so if you pluck off those two H's, and those two H's came off of that O and that C, what are you going to put in between that C and that O? Because it had a single bond, but now it has a double bond. And is this H that H? And would we again call that an aldehyde? And are aldehydes also susceptible to oxidation? Only now the mode of oxidation is you simply insert O. Where do you insert the O? In between the C and the H. And when you insert O in there, does the aldehyde become an acid? And so if you see this schematic with that in brackets, that means it goes through that species, but we wouldn't isolate that species because it's going to keep going. But it happens stepwise. Okay, so onward to this alcohol. One quick review. What makes this a primary alcohol? C, which pairs the O, is only directly connected to one other C. This alcohol up here, the C, which pairs the O, is connected to no other C, so we call that a methyl alcohol. And what would we say this alcohol is classified as? Thank you, Tasha. She said secondary, and she's speaking of that C being directly connected to two other C's. And again, what's going to be our oxidizing system? Chrome 6 in acid, and that's your cue to rip off two H's. And which two H's? That one, and one on this C, one on that C, or one on that C? That C. So if you want, can you draw it in? And if you rip off those two H's, where do you put the new double bond? Between this C, which is that C, this O, which is that O. And so now you quickly ascertain what functional group is that. It's a ketone. And would ketones further oxidize? Not easily. So you can envision lots of questions like, why does this alcohol give you a ketone and this alcohol goes through an aldehyde onto an acid? Tasha says that one gives you a ketone because this one primary gives you initially an aldehyde and then an acid. And then lastly, on to this alcohol, and what would we classify it as? Tertiary. So if we're going to try to oxidize that, we would try chromium 6 in acid, and why would we get no reaction? So you don't want to try to memorize all that. You want to have a system for when something is oxidizable or not. So that's what I would say is a good question to ask yourself. If a C has an O, and that same C also has an H, then it can be oxidized. So if we put this loose definition in play, does this C have an O? Does that C have an H? Can it oxidize? Fast forward to this C. Does it have an O? It has an O, but does that C have an H directly connected on it? So if the C with the O does not have an H on it, then not easily oxidized. Makes sense? So if we go to this one, does that C have an O? That C has an O, does that C have an H? So can it oxidize? Yes. How about this molecule? Does that C have an O? But does that C have an H? So why don't ketones easily oxidize? The C with the O doesn't have an H. Why do aldehydes and primary and secondary alcohols oxidize? So that's basically oxidation of alcohols, but can we also now understand that oxidation of alcohols is a way to make acids and or ketones? And last time did we learn that if we have an aldehyde or a ketone and we do a reduction, do we get our alcohol back? So in other words, that's oxidation. If we wanted to go that way, what would we do to this ketone to make that alcohol? Sodium borohydride. So oxidation and reduction, hopefully from general chemistry, you got that they're just reverses of each other, still true in organic. It's just that now we're using different things to cause the oxidation and reduction. You're not responsible for the mechanism. They're complicated. And of course, the chromium 6 is an old school reagent. It's a very potent oxidant. Modern times says we have modern oxidation agents which are much more efficient, and some of them can even stop and give us the aldehyde if we want. So we're not going to be responsible for that because I'm always going to use the Chrome 6, but just bear in mind that if you wanted to convert a primary alcohol to an aldehyde and stop right there, you could do it, just not with that chromium 6 reagent. And while they're on the board, what would we call this alcohol? Methanol. What would we call this aldehyde? Methanal, or also known as formaldehyde. And what would we call this acid?
Methanoic acid.
Or formic acid. What would we call that alcohol? Ethanol, ethanal, or acetaldehyde, and ethanoic acid, common name acetic acid. And would we call this 2-propanol, also known as isopropanol, and 2-propanone, also known as acetone? And this alcohol, 2-propanol or tert butyl alcohol. I'm going to leave that on the board for a second. Yes, Tasha? Let's just say that if we take ethanol and we oxidize it, it's going to get converted to acetaldehyde, but it's going to keep going to acetic acid. We're not going to be able to stop here. So shifting gears to this board, would we say these conditions are and if we go back to this board, those conditions are going to be dehydration. So when you see this, this is generic for heat. You should think loss of water. And I get why it's confusing. And you definitely don't want to confuse this with this. So in oxidation, overall, what are we stripping off the alcohol? H and H. If we do get an aldehyde, then the mode of oxidation is insert O. So really, that's what happens overall in oxidation. You either strip off two H's or you insert an O in between an oxidizable CH bond. You don't want to confuse either of those with this. So in dehydration, are we looking for H and OH?
Yes.
Yes. So over here, did I circle the whole OH or just the H? But over here, what do you want me to circle?
OH.
OH. And then you can ask yourself, who lost the OH? At C. So do you also lose the H from that same C? Or do you lose the H from an adjacent C? You lose the H from an adjacent C, and in that example, do we have two adjacent C's? And if you want, can you draw your H in on that and that? And of course, there may be more than just the one I've drawn in. And so if I circle that one, which will give us the Zaitsev product, light bulbs should be going off, because if we dehydrate, are we going to make an alkene? And what did Zaitsev say about which alkene we make? The more substituted is the more stable and the predominant product. So if we lose that H and that OH from between this C and that C, if that leaves, those come in there, are we going to make that alkene? If we were to lose this H off that C as that OH leaves, then we would make that alkene. And which is more substituted?
The first one.
So this is Zaitsev and this is Hoffman, and this one would predominate. So this is really nothing new. It's probably prudent if I go through how it happens to sort of get a review for a final. If I go mechanistically with that, the O of the alcohol is going to pick up a proton from the dehydration system. Would we say we now have protonated water? And is that now a good leaving group? And with loss of water, we could make that carbocation. And then either that H gets flipped off, forming that alkene, or that H gets flipped off, forming that alkene. So the thought there is, if we try to kick off OH by itself, you would be trying to remove OH minus. And would you say that's a good leaving group? No. But as soon as we put an extra proton on the OH and make the water's oxygen positive, then can we remove water as a neutral molecule, not OH, and then your water is a good leaving group. And then does it also make sense that this is a secondary carbon? So is it possible to form a secondary carbocation? And then lastly, if I say, what overall type of mechanism would you say that's going through? SN1, SN2, E1, or E2? That's E1. So you can think of dehydration of alcohols to alkenes just as you thought of with the analogous halide. So when we did alkyl halide eliminations, what did we use to do that same reaction? We took the halide and reacted it with a base. So with alcohol, it sort of flows that you can do the same sort of thing, only now you're just protonating to make a good leaving group. So how in your mind are you going to know whether to lose water, make an alkene, or to oxidize? Based on that, if you see the chrome 6, you're doing oxidation. If you see acid, water, and heat, you're doing dehydration. So if we took that just to practice, are we going to oxidize or dehydrate?
Dehydrate.
Dehydrate. And so once you know you're dehydrating, you look for H and OH. The OH is pretty easy to find. That OH is currently connected to that C. So now you're looking for H, and you look to the adjacent carbon. So if this is the C with the OH, there's the adjacent carbon and its C. And once you pluck those two off, what do you put in between the two carbons that lost H and OH?
A plus one? No. Oh, a double bond.
Yep. That's the overall reaction. Would this one go through a carbocation? That one would not, because this carbon is primary and those aren't going to form carbocations. So all that business about E1 or E2 is still in play. This one would be more of like an E2 mechanism where the H, well, first the OH is going to get protonated to form a positively charged water, but then the water of that system is going to act as a base and the elimination happens simultaneously. So it's more like E2. And now to make sure we've delved into the details, the literature always uses these two numbers. In case you come across this on future tests. The higher the temperature, the more you favor the alkene. If you do it at a lower temperature, the more you favor the ether. And the ether is quite counterintuitive. Different it is going to happen than the alkene. Because the alkene, we're kind of getting used to eliminations to make alkenes, because that was all of chapter 6 and 7. But we haven't really talked about how to make ethers yet. But if you see acid, maybe water, and heat, but the heat is now specified at 140, you should think we're going to make an ether. So if we're still treating that alcohol, how in the world do we make an ether from that alcohol? Really quite easy. You just say, now I'm not going to get the H and OH from one molecule. I'm going to draw the mirror, put up another molecule of the same alcohol, and strip off H from one and OH from the other. And from this molecule, would we say this O lost the H? And from this molecule, would we say this C lost the OH? So now what do we connect together on the other side for the organic product? That C to that O. And then is it clearly recognizable as an ether? So that's confusing for sure. Let's take that molecule and practice 3. Chrome 6, acid, water, heat at 140, and acid, water, heat at 180. So if we start with the same alcohol, but now we're going to do it, your job is to recognize this is dehydration or oxidation.
Oxidation.
Oxidation, and so are we going to lose this H and that H?
Yes.
And are we going to make a double bond in between the C, which lost the H, and the O, which lost the H, call it a ketone, and ask ourselves, does this C, which has an O, also have an H, or is it as oxidized as it can get and it's not going any further?
It cannot go any further.
Go any further, it's a ketone, stops right there. If we have these conditions, it's dehydration, and this specific temperature says make ether or make alkene. Make ether. To make ether, what I suggest is draw your alcohol, draw the alcohol again, and pluck off H from one and OH from the other. So if I say, let's take this molecule and remove H, and let's take this molecule and remove OH, and we would say this O is losing H, this C is losing OH, and what are you going to connect together to make the ether? The O which lost the H and the C which lost the OH. And here we have the classic COC bonding, which is an ether. Not to be confused with this, which is the same acid and heat, but now we're hotter. And when we go hotter, we should think alkene. And when you make your alkene, of course, do you lose the OH off of one C and the H off the adjacent C? And so now if you have your H and OH highlighted, circled, what happens in between the two C's, which lost the OH and the H? double bond. So to summarize that, we're going to say alcohol reactions, oxidation, we use this system. And a primary alcohol will go into an aldehyde and then onward to an acid. A secondary alcohol is going to oxidize into what? A ketone, and stop right there. And what about a tertiary alcohol? Not going to oxidize. And when we go to dehydration, you've just got to be aware of the actual temperature specified in the problem. The 180 says make what? An alkene. The 140 says make what? An ether. And to make the ether, again, do you need two molecules of the same alcohol, H from one, OH from the other, connected up? When you make the ene, the H and the OH come off from within the same molecule. SN2, this is largely a review. If I go with that and you see something like that, you've got to use the fundamental thing about acids and alcohols that we just learned, in that this O with this H, this is not oxidation, but it is protonation. And so if this O picks up a proton, could we convert it to that positively charged thing? And if it's really mechanistically like that, the proton ends up on the O, giving us a really good leaving group. And did we also make a negatively charged chloride? And from all our past chemistry, is this chloride a good nucleophile? So what do you guess could happen with a good nucleophile on a carbon that has a good leaving group? So would that be another way to convert an alcohol to a halide? And of course, depending on the original carbon skeleton, it could be SN1 or SN2 like. So that's really just sort of a review, just to know that if you have alcohols, can you make them into halides? If you have halides, can you make them into alcohols? So those two processes are reversible. And we studied that a long time ago. And then the last one, which are these, I don't know if we've ever used the word alkoxide before, but have we used potassium butoxide a whole bunch as our highly hindered base? And have we used, say, sodium ethoxide? Those are called alkoxides because the O of what was an alcohol is now deprotonated. So since we're on the alcohols, if you just take ethanol with sodium metal, you get hydrogen gas that bubbles out plus that alkoxide. And what we're picking up here on is if we go to the final exam, and do we always have to show this sodium counterion? Could we show this as what it really is? Could we, of course, show the counterion if we want to? In that case, sodium. So if I go with which is more nucleophilic, this or this? We're right back to chapter 6 with which is a better nucleophile, the negative species or the one that's not negative. That's a better nucleophile. Which is a better base? So the negative thing is always a stronger nucleophile and a better base. If you wanted to do classic SN2 chemistry really quickly, would you use this? Could you use this if you could cook it for a longer period of time and you had the right halide? So what we're picking up on here in this section is how do we convert ethanol to ethoxide? If it's just called an alkoxide in general, if it's just an R group. And the way you do it is you just throw in a column 1 metal. So either potassium or sodium. So how would we make potassium tert butoxide? You would take tert butanol and throw in what? Potassium. Then what would we make? Potassium tert butoxide, and would we say that's a potent nucleophile? Or it's too hindered to be a really good nucleophile? But is it a potent base, which is hindered, and that's okay to still be a good base? So those are reactions of alcohols. Of those 4, which ones are really new? The SN2 is that's sort of just a review for the final exam. Probably done this before. Make sure we got it. Classic carboxylic acid. Which one? Ethanoic. Which acid is that?
Benzoic.
Benzoic. Anytime we have a nitrogen connected to 1, 2, or 3 carbon groups, those are classified as amines. Which amine would that be? Methylamine. This is dimethylamine. This is trimethylamine. So in naming amines, do you just name the carbon groups? It's been a while since we did that. Just for all, since he chimed in, what would that amine be? That's ethylamine. How about that one? Isopropylamine. How about that one? Hexbutylamine. Isobutylamine and terbutylamine. So when we used week one, when we made acid analyte, phenylamine or aniline, common name. Definitely not to be confused with that one, which is benzylamine. So these two functional groups are going to be key for understanding all of your biologic molecules. So the first thing we want to cover is just their acid-base chemistry. So carboxylic acids, as the name implies, are acidic. So what that means is either of those acids, if they are shown some sodium hydroxide, are going to deprotonate. We'll get a proton transfer from the acid to the base. When an acid loses its proton, it forms what we call a carboxylate ion. If we want to show the complete reaction in totality, proton would end up on the OH. That's going to make water. The sodium would part ways with the hydroxide and be the counter ion to the carboxylate. So if this is acetic acid, and this is the carboxylate of acetic acid, and specifically the sodium carboxylate. Tasha weighed out for us 50 grams of it the other day for our lab. Is that called sodium acetate? So these are named just like we named esters. All sort of what that is, then the acid name with an 8 ending. Sodium acetate, and the acetate's origin is acetic acid. So if we practice that, what's this going to be converted into if we throw in a base? Proton goes away, and you would have decarboxylate. And in this case, did I use a specific base or generic? If I used KOH, then what would be the exact products? The potassium would be the counter ion to the benzoic acid, and that would be potassium benzoate. And where would the H go that was on the acid? To the OH to make water. And this is critically important for many reasons. One of them is solubility. So this is an ionic compound, just so is that. These ionic compounds are going to be far more water soluble than their corresponding protonated versions. So this isn't really synthesis, this is just the properties of a carboxylic acid. And equally important, if we added base to go that way, could we take this and add something to go back that way? What would we add to go back that way? That's exactly what we did in our benzocaine synthesis. Contrary to that, your amines is really the only basic functional group that we speak of. And when we say amines are bases, they are bases because all of these nitrogens have a lone pair. And that lone pair of electrons is free to act as a base. And so if we want to take methylamine, we could show it like that or like that. This way is going to be far more helpful if you need to show a mechanism. And if we're trying to understand why amines are basic, we're just going to show a reaction with a classic protic acid. So now the amine nitrogen would pick up the proton, and therefore, which way do these electrons have to go? With the chloride, and if structurally we would get that and that, and I'm not complete because if something's negative, something's positive, who would have used a pair to make a new bond to a proton? The nitrogen. And if this nitrogen didn't start off positive, is it now positive in that species? If we wanted to just show this using formulas, then it's just commonly shown like that. And like on a medicine label, you'll also see it shown just like so. That's what we would call an ammonium chloride or an amine salt or an amine hydrochloride. And the reason they form is again because these amines are basic and they will pick up a proton from an acid forming a salt. And again, that's not really a synthesis, it's an acid-base property. So we would call this the free amine or the free base. This is the hydrochloride salt. Which one would be more soluble because it's ionic? That one right there. If you had the hydrochloride salt, what would you use to convert it back to the free base? If you added acid to make it go that way, what would you add to make it go that way? A base. So amines are critically important because are they present in almost every biologically active substance, aka your medicines and drugs? And if you want to take your medicine in a pill form, is it helpful that they're water soluble? So if the free base amine is not very water soluble because the carbon group's much bigger than methylamine, could you convert it to the hydrochloride to give it some water solubility? And then since this is reversible, if the free base is the active form in the body, there's still enough of it to do the job. So that's what I wanted to cover today was this, and then these properties of those two functional groups. So on Friday, we're going to review esters and amides. And then go over the macromolecule handout, because this is really important in the macromolecules. Are your carbs, lipids, amino acids and proteins, and nucleic acids. By Friday, I'll have you a handout on practice problems. Anyone have questions? Anyone in Mexico have questions?
I don't.
Okay. All right. Well, I'm glad you made it, and I hope you feel better, Valeria.
Thank you.
Enjoy your cruise. I think you're muted.
Were you able to record this too? If you want to rewatch it?
Yeah, I hope it's being recorded. So I'm gonna end the session, and then hopefully, usually the recording is available within 24 hours. As soon as I
Thank
get
you.
it, I'll put it on the YouTube.
Thank you.
Thank you, Professor. I have a question. Under the first, under alcohol preps, number 1, I see the R, but I don't see. Is that? I can't see what's after that. Yes.
That's just a review of when we had a halide like that, and we
Yes.
wanted to make add alcohol.
Okay.
Would we use water and/or hydroxide and do SN2 chemistry?
Okay.
So that's way
Oh, so
back
that's,
in chapter 4 or chapter 6 or chapter 7, right?
okay. So that's R/X.
X.
Okay. Okay.
It's just converting a halide to an alcohol.
Okay.
So it's SN2.
Thank you.
So that was a review. And hydration of alkenes, that was what we just got done covering in chapter 7. But oxymercuration, demercuration, and hydroboration oxidation are ways to make alcohols from enes.
Okay. Okay. Thank you very much.
Okay, I'm going to end it. See you, Rose.
Okay.
Bye.
Okay. Bye-bye. Thanks.
Okay.